All right, our state standard that we're working on is adding and subtracting fractions with like and unlike denominators. Today what we're going to do is we're going to reverse it. I've already taught basic and I've taught proficient. And I've made videos on them that you can go and look. Today I'm going to dive specifically more into an advanced problem. An advanced problem with unlike denominators with dividing. With unlike denominators with borrowing. This will be one of the most challenging problems that you will see on your SBAC test. So take very good notes, and if you are curious about something, I'll press pause and answer questions. But let's get started. With an advanced problem, we know we're dealing with mixed numbers. And we're subtracting a fraction that has a different denominator. And when we have a different denominator, we're talking about different size pieces, right? So we can't really compare, subtract, because 3/7, is that almost nothing, almost half, or almost a whole?
Almost a half.
And 4/5, is that almost nothing, almost half, or almost a whole?
Whole.
So how can we subtract 3 and 4? How can we even compare them? The very first thing that we must do, that we learned in our proficient examples, is that we have to get congruent denominators. We have to have similar sizes before we can add or subtract. It's comparing apples to apples and oranges to oranges. And by making sure that we have similar denominators, that's very, very important. Now I'm going to do it in a bar model, and then I will show you for the first time the algorithm. And that's why I'm making this video, that those of you that might not remember the algorithm right off the bat, you will be able to refer to this video. Now, the bar model is if I have one whole, and then I have a whole that's cut up into 1, 2, 3, 4, 5, 6, 7, and I have 3 of those 7, I'm subtracting 4/5. So what I'm going to do is I'm going to cut this up into 1, 2, 3, 4, and I have 4 of those fifths. Can you see that? 1, 2, 3. Oh wait, 1, 2, 3. Oh, I needed one more. Sorry about that. So according to our bar models, you all can see how many of these. 1, 2, 3, 4 out of 1, 2, 3, 4, 5. Look how many boxes I have. That's 1, 2, 3, 4, 5, 6, 7 times 1, 2, 3, 4. That's 28 of these congruent size squares that I need to subtract. Can I subtract 28 from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 that I had in the 3/7? No, I can't. I can't do that.
So you're gonna have to.
So what I'm going to have to do is I'm going to have to cut the whole up. And when I cut this whole up, I'm going to cut this whole up into 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, 7. So now I have congruent size pieces. I've cut that whole up into the equal sizes. So now watch. I'm going to let's review this. And I'm going to put dots in each one of these so we can see here. This 1 3/7, can you see that right here I have 3 out of 7. So my numerator would be the 3 rows here, and that's out of the 7 rows here. Are you all with me?
Mm-hmm.
And then I'm subtracting the 4/5. Well, that's 1, 2, 3, 4 out of the 5. Well, look, how many dots did I say I had in the 4/5?
28.
28. So I'm going to subtract 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Now how many do I have left over? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. But my denominator, my whole, is still cut up into how many pieces? Well, what's 1, 2, 3, 4, 5 times 7?
35.
So that would still be 35. So my answer of 1 and 3/7 minus 4/5 is 22 out of 35. Well, does that coincide with my estimated solution? Here I had 1.5 estimated about 1.5, and I subtracted about 1, and I was left with about half. Is 22 out of 35 about half?
Yes.
So my estimated solution confirms that my final solution is in the ballpark. Isn't that pretty cool? Now, the reason I picked this fraction in particular is because we're dealing with a lot of boxes here, right? Bar models were great to give you a concrete representation of what was actually going on. But we're going to have to eventually transition, especially when we get numbers this big, we have to transition to an algorithm, a mathematical way of doing what I did here. And so in this particular example, I'm going to do the same thing, but I'm going to do it in the form of an algorithm. Now the algorithm starts, you have to stack your fractions. You have to. You got to stack your fractions. In other words, instead of having 1 and 3/7 minus 4/5 written like this, I rewrite it like this. Make sure you put that in your notes. That's important to do. Because now that I've done this, what I'm going to do is I'm going to put a fraction bar, or a division sign, because all fractions are division problems, right? And I'm going to do this so I can put my equivalent fractions over here. Now we know from my bar model what will my least common denominator be.
35.
We know it will be 35. If I'm not sure what my least common denominator is going to be,
You can look at the multiples.
yeah, my multiples for 7 would be 7, 21, or no, 14, 21, 28, 35, and 5 is 5, 10, 15, 20, 25, 30, 35. Oh, it's 35. So you could do it that way, but because we did our bar models and our knowledge of our times tables, we know that it's going to be 35. Are you with me all? Good. So now what you need to do is you need to ask yourself, what did I do to 5 to get to 35? Multiply it by 7. And whatever, in this algorithm, whatever I do to the bottom, I gotta do to the
Top.
So what's 4 times 7?
28.
Now I know that 4/5 is congruent to 28/35. Those are equivalent fractions. It is the same value. That was the real power of the bar models, that you saw that that square didn't become any bigger. I just cut it up into more pieces, right? That's what I did here. Now we do the same thing to the top fraction. 7 times what gives me 35?
5.
And whatever I do to the bottom, I got to do to the
Top.
What's 3 times 5? Ah, now I have the algorithm that does the same thing that the bar model did. Now, what do you think would be a possible answer that the SBAC will put on there that will try to trick you? Ethan?
Wait, it might
13.
be
13.
13.
How many of you agree with those brilliant kids that a possible SBAC answer will be 1 and 13/35 or 13/35? Because they are going to assume kids are just going to subtract 15 from 28. And remember, I told you, you have to remember that 28 would be like kids knowing that there's pizza up top, and they each need a piece of pizza. Can 28 kids reach up and grab enough pizza here to No. It is always 15 minus 28. Now, right now, can I subtract 28 from 15?
No.
If I had 28 kids down here and they want to reach up and grab 28 pieces of pizza, can they do that?
No.
No. So what do we end up calling in?
Pizza man.
The pizza man or woman. And here we go, everybody, count of 3. 1, 2, 3. Pizza, pizza! And we take one of these. This is where the magic happens.
And slap it.
We take this hole right here and we convert it into a pizza and we slap it on our paper. And right there's our pizza. Ah, pizza, pizza. Can you smell the pepperoni and cheese?
Yeah.
But wait a minute, this is a hole. This is a hole. And I want to make sure that all of my pieces are congruent. What am I going to do with this pizza? I'm going to cut it up into 35 pieces. Why? Why 35? Why didn't I do
Because-
15?
Because the denominator is 35.
Yes. If the denominators were 12, what would I have cut this pizza up into?
12.
If this denominator was 100, what would I have cut this pizza up into?
100.
But wait a minute, this is a whole. What do we know about fractions? The relationship between the numerator and the denominator that makes up a whole.
The numerator is how many parts is in the whole.
The numerator is how many parts in the whole. And if the whole's cut up into 35, how many parts would equal a whole pizza?
35.
Right. So I know I'm going to cut this pizza up into 35 equal pieces, and I'm going to have all those pieces. So now what I'm going to do is I'm going to add the 35 plus the 15. Because now I have this many pieces of pizza. What's 15 plus 35?
50. Yeah, it's 50.
So now I have 50, and now do I have a bigger number on top than on the bottom?
Yes.
I do. What is 50 minus 28?
22.
22, and my denominator stays the same because that's how many slices of pizza has been cut up into. So look at that. Now can you see the correlation between the bar model and the algorithm? Okay, so I'm going to stop the video here, but this will be an example of borrowing with fractions that you can refer to if you need to. All right? All right.